we conclude this lesson with a few important remarks. The first remark is about the trick called memoization. Usually when designing a dynamic programming algorithm, you start with analyzing the structure of an optimal solution for your computational problem. You do this to come up with the right definition of a subproblem that will allow you to express the solution for a subproblem through solutions for smaller subproblems. So when you write down this recurrence relation, you can actually transform it to an either iterative algorithm or a recursive algorithm. The corresponding iterative algorithm just solves all subproblems, going from smaller ones to larger ones. And for this reason, it is sometimes also called a bottom-up algorithm. On the other hand, the recursive algorithm to solve a subproblem makes recursive calls to smaller subproblems. And for this reason, it is sometimes called a top-down approach. Well, if you implement a recursive algorithm straightforwardly, it might turn out to be very slow because it will recompute some values many times, like with Fibonacci numbers, for example. However, there is a simple trick, and it is called memoization, that allows you to avoid recomputing many times the same thing. Namely, you can do the following. When solving some subproblems, right after solving it, you store its solution into a table, for example. And when you need to solve when you make a recursive call to solve some subproblem, before trying to solve it, you check in a table whether its solution is already stored. And if its solution is already in the table, which means that it was already computed, then you just return it immediately. So this recursive call turns out to be just a table lookup. So this is how a recursive algorithm with memoization works. Let's see how a recursive algorithm with memoization for the knapsack problem looks like. For simplicity, let's assume that we're talking about the knapsack with repetitions. In this case, we need to compute our subproblem for a knapsack of size W is just the optimal value for the knapsack of total weight W. So we compute it as follows. We compute it by a recursive procedure. First of all, we check whether its solution is already in a hash table. So we use hash table to store pairs of objects. So for weight W, we store value of W if it is already computed. If it is already in the table, we return it immediately. Otherwise, we just compute it and we make recursive calls to compute the values for the subproblem on W minus Wi. Okay? And when the value is computed, we just store it in our hash table. Right? So this way, we use memoization by storing this in the hash table to avoid recomputing the same thing once again. So once again, an iterative algorithm solves all subproblems going from smaller ones to larger ones, right? And eventually solves the initial problem. On the other hand, the recursive algorithm goes as follows. So it starts from the initial problem and it makes recursive calls to smaller subproblems. Right? So in some sense, an iterative algorithm and a recursive algorithm are doing the same job, especially if we need to solve just all the range of subproblems. However, a recursive algorithm might turn to be slightly slower because it solves the same subproblems on one hand. On the other hand, when making a recursive call, you also need to put the return address on stack, for example. So a recursive algorithm has some overhead. There are, however, cases when you do not need to solve all the subproblems. And the knapsack problem is a nice illustration of this situation. So imagine that we are given an input to the knapsack problem where all the weights of n items together with the total weight of the knapsack are divisible by 100, for example. This means that we are actually not interested in subproblems where the weight of the knapsack is not divisible by 100. Why is that? Well, just because for any subset of items, since all the weights of items is divisible by 100, their total weight is also divisible by 100. So in this case, an iterative algorithm still will solve just all the range of sub-problems, while a recursive algorithm will make only those recursive calls that are actually needed to compute the final solution. So it will make only recursive calls to sub-problems whose weight are divisible by 100. The final remark of this lesson is about the running time. So as you remember, the running time of both algorithms that we designed in this lesson was big O of n multiplied by w. And this running time looks like polynomial. However, it is not, and this is why. So consider, for example, the following input. Assume that the total weight of the knapsack is as shown on the slide. This is a very huge number, roughly 10 to the 20. 20 digits of decimal representation. At the same time, the input size is really tiny, just 20 digits, right? So this is not gigabytes of data, just 20 digits, but on this input already, our algorithm will need to perform roughly 10 to the 20 operations, right? This is really huge. For example, we cannot do this on our laptops. And this is because to represent the value of w, we only need log w digits, right? So in case of the knapsack problem, our input is proportional not to n plus w, but to n plus log w. Okay, and if you represent the running time in terms of n and log w, then you get the following expression, n multiplied by 2 to the log w, which means that our algorithm is in fact exponential time algorithm. Put it otherwise, it can only process inputs where w is not large enough, is roughly less than 1 billion, for example. Okay, and in fact, we believe that it is very difficult to construct an algorithm that will solve this problem in polynomial time, in truly polynomial time. In particular, we will learn later in this specialization that this problem is considered to be so difficult that for solving the knapsack problem, for example, in polynomial time, one gets $1 million.